So now we're going to look at what happens when you apply the Newton method to the Rayleigh quotient. So if you recall, we had sort of introduced this idea of the generalized Rayleigh quotient, um, which allows you to compute not just the, it's like the minimum eigenvalue. And this involves this trace of y transpose A y, y transpose B, y inverse. Right, this is for the matrix pencil case. So we're going to specialize this to the case and then y is over r n by p. We're going to specialize it to the case that p is equal to 1, right, and b is the identity matrix. Okay, and so this gives you then a map from F, which is Rn star. So this is basically just Rn with the origin excluded, okay, to R. So Rn star is Rn with the origin excluded. Okay, so this is a map from y to f of y, which is just y transpose ay divided by y transpose y. Okay. Yep. Okay. Yes. So this is the Rayleigh quotient of A. I mean, you can think of this as an optimization of manifolds problem because this technically is not a vector space because the origin is excluded, but it's not that exciting. So that's not such a big deal. What's perhaps a bigger deal is that what's perhaps a bigger deal is that when you apply the Newton method, it's like to this cost function, bad things happen. Okay, so let's see what happens. Well, before I state that, so again, the problem is that the Rayleigh quotient is scale invariant. So the minimizers are not isolated. Okay, and that gives you a problem. Okay, so let's see what happens when you apply the Newton method to this. Okay, Newton's method. Applied to this function. Right. Okay, yields the following iteration. Y gets mapped to 2y for every y such that f of y is not an eigenvalue. Of A. Okay, and the proof just involves calculating the gradient and the Hessian. So you can check that the gradient of f of y is equal to 2 over y transpose y, ay minus fy y, and the Hessian f of y in the direction z is equal to the linearization of the gradient of f okay, and this is equal to 2 y transpose y az minus fy y minus 4 over y transpose y squared y transpose a zy plus y transpose z a y minus 2f y transpose zy. Okay, let me just try to finish that. So this is equal to Hessian is equal to 2 over y transpose y, identity minus 2 y transpose over y transpose y multiplied into a minus f y times the identity minus 2 y transpose over y transpose y. Okay, so the whole thing times z. So let's call this thing in the parentheses hy. Okay, so hy is singular if and only if fy is an eigenvalue. Of A. Okay, and then when that's not the case, right, the Newton equation which is that hy times the update is equal to negative the gradient of f of y, right? Has only one solution, and it turns out that the update is equal to y. Okay, so the Newton update goes from yn to yn plus yn, which is 2yn. Okay, so that's interesting, right? So what that's more or less saying is that when you do this Newton method, it's like on the Rayleigh quotient, all it does is to rescale, it's like the iterate by a factor of 2. Okay, so it doesn't actually sort of do anything interesting to the problem, which is of course problematic, right? So this method is not going to converge. Newton's method is not going to converge for the Rayleigh quotient. Okay. So and it turns out that this problem is in some sense not specific to just the Rayleigh quotient, right? So this issue where the Newton method fails is not unique to the Rayleigh quotient. Okay, so it holds for any f which is homogeneous of degree 0. And what that means basically is that if you take f and you evaluate it on y times alpha, well, let me just put it as alpha y, that this is equal to just f of y for any real alpha not equal to 0. Okay, so so this is an interesting problem. So there's sort of, again, two approaches to deal with it. One is to restrict, it's like f to a subset of Rn star, right? So we can restrict f to a subset m of Rn star such that any ray y times r star. So, all right, so again, the problem, if you will, is that if this is the origin, right, this whole ray of points, right, actually both directions, if you will, right, have the same Rayleigh quotient, okay? So what you can do is that you can choose some subset so that it intersects every ray only a finite number of times. So you can choose m such that okay, so any ray intersects m at least once. So there has to be a representative for every ray, and only finitely many times. Okay, so the effect of it intersecting once but only finitely many times then is that all these, copies of the same minimizer, in some sense, are disjoint from each other. Okay, so this guarantees implies the minimizers isolated from each other. Okay, which is sort of what you want. And then, as you might imagine, one very natural way to do this is to just look at the unit sphere. Okay, so we can consider which is just Sn minus 1 is the set of y in Rn such that the norm of y is equal to 1. Okay, and then restricting the Rayleigh quotient to Sn minus 1, right, gives a well-behaved cost function with isolated minimizers. And the problem, of course, is that you lose this linear space property. And then what we're going to do, it's like in the course of this class, is to talk about how to do, how to deal with these kind of nonlinear manifolds. It's like using the method of embedded manifolds. So we'll see how to handle this. As an embedded manifold. Okay, and then and again, the other approach is to think of this as a quotient space. And again, the right thing to do is to think of this as the rail projective space, right? So we can also consider a quotient space approach on the rail projective space. And right, and we'll see more generally how to handle quotient manifolds. Okay. And I should just say that for the purposes of the Rayleigh quotient, it's like operationally, these two approaches are not going to be that different, but the quotient manifold approach is going to be much nicer when you deal with things like the Grassmannians. Okay, so for the two-sphere, for the sphere, right, the methods are not that different. In practice. But for the Grassmann space, the Grassmann manifold, the quotient manifold approach is much more natural. Okay, so, all right. So anyway, so let me just stop here for now.